Hello, I'm Prajakta and we'll be exploring sheet metal forming today. So what is sheet forming? Sheet metal forming is one of the most widely used processes in manufacturing today. It involves reshaping thin flat sheets of metal into functional parts using plastic deformation. What's unique is that we aren't adding or removing any material. Instead, we are changing the shape of the sheet using force, usually through dies, punches, or rollers. We categorize flat metal sheets based on their thickness. So if the thickness is less than 0.2 millimeters, it's called foil. The thicknesses between 0.2 mm to 6 mm are called sheets. And this is the most common category we work with. Anything greater than 6 millimeters is called a plate. These distinctions help us understand what processes and tools are appropriate for a given application. Sheet metal forming is especially valuable for producing lightweight, strong components quickly and efficiently. It's essential for industries that rely on scalable, repeatable manufacturing. Sheet metal is just all around us. You name the industry and you have sheet metal there. An automobile industry is used in car doors, hoods, trunk lids, chassis, reinforcements, and underbody panels. In beverage and packaging industry, sheet metal is deep drawn into aluminum cans for drinks and food storage. In aerospace, it forms the skin panels of the fuselage, turbine engine shells, and interior panels. In construction, sheet metal is used for building panels, roofing, cladding, and ductwork. For aesthetic application, it provides seamless and polished surfaces on consumer electronics. In electronic industry, it's widely used for making enclosures, heat shields, and mounting brackets for devices like laptops, routers, and control panels. You'll ask why sheet metal forming is so popular. First, it's material efficient. Since we are reshaping the material instead of cutting it away, there's very little scrap. Second, it supports extremely high production speeds, which is perfect for mass production. It also produces parts that are both lightweight and strong. Surface finish is often excellent, meaning parts can go straight to assembly without secondary operations. The tooling once built allows for cost-effective production at scale, and because the process supports complex shapes, design flexibility is quite high. All these reasons combined make sheet metal forming one of the most economical and versatile processes in manufacturing. So to understand how sheet metals behave, we need to first take a look at how it's made. Sheets are produced by rolling, hot or cold, through a series of rollers that compress and elongate the metal. This aligns the grains in one direction and makes the metal stronger in that direction. So this introduces a phenomena which is called anisotropy, which means the material's mechanical properties vary based on direction. So if we form or bend the sheets along the same direction as the rolling, the part is more likely to crack or wrinkle. But when we bend the material perpendicular to the grain direction, it helps achieve a cleaner result. Now let's take a look at the 5 material properties that really influence how sheet behaves during forming. So ductility, as we know, is the ability of the material to undergo plastic deformation before failure. But in terms of sheet metal, the higher ductility allows it to be drawn or stretched into more complex parts without cracking, especially relevant in processes like drawing or stretch forming. So malleability is the sheet's ability to be compressed without cracking. It's critical in bending and deep drawing again. Yield strength is the stress at which the material starts to deform permanently. So lower yield strength generally means that the material is easy to form. Ultimate tensile strength tells us the maximum stress the material can handle before failing. So it's useful to know the forming limitations, like how much force is needed to break the material and which indirectly tells us how much tonnage the machine requires. The elastic modulus affects the spring back tendency of the material to return to its original shape after bending. So a high modulus means more spring back, which requires compensation in tooling design. This helps us. The diagram here shows how grain alignment impacts formability. Bending along the grain often leads to crack, while bending across it improves the result. We can also see how drawing ratio varies along different materials as a result of anisotropy. So the short chart below shows us how to compare deep drawing. For instance, materials like titanium or steel or aluminum and deep drawing quality steel show higher drawing ratios, making them easier to draw into complex shapes. While in contrast, materials with low drawability require more careful design to avoid tearing or failure during formation. So let's go over the most popular forming processes. First, we have bending. This is where we deform the sheet along a straight line to create an angle. So V bends usually a V-shaped punch and a die, while U bending creates a U profile. You'll see this in brackets and chassis parts usually. The next is deep drawing. We pull a sheet into a die cavity using a punch to make a deep hollow shape. This is how we make sinks, beverage cans, and automobile fuel tanks. Stamping is a fast, precise process where sheet is pressed or sheared between a punch and a die. This is a normal cutting operation. It's ideal for high-speed production. A common stamping operations include punching or piercing to create holes, blanking to cut out a part, notching, which is used to remove the material from the edges, and lancing, which is used to partially cut and bend the material in one stroke. Then we have roll forming, which is a continuous process where the sheet passes through a series of rollers, where each one incrementally shapes the material until the final cross section is formed. This step-by-step shaping allows complex constant profile parts to be produced efficiently, like door frames or beams and structural rails. Next, we have embossing and coining. So embossing creates raises or recedes design on sheet surfaces, often for textures, logos, or grip enhancement. Coining is a high pressure forming technique that produces sharp, detailed surface features like patterns or edges. Then we have stretch forming, which pulls the sheet in tension while it's wrapped over a die, allowing large, smooth contoured shapes like wing panels or architectural elements to be formed with excellent surface finish. Now that we went through sheet metal forming processes, let's get into the guidelines. Designing for bending begins with bend radius. It is a critical rule that inside bend radius should be at least equal to the material thickness. If you're using a smaller radius, it risks surface cracking on the outer side and compression bulking on the inner side. There's also a direct relationship between the material's hardness and the minimum bend size required. If you see the table, the harder the material, the larger the minimum bend radius must be. So for example, soft aluminum alloys can be bent with tighter radius, while harder materials like stainless steel require much larger bend radius. The table correlates Rockwell hardness values with recommended bend radii in terms of material thickness T. So you can see in the diagram shows what happens when the bend radius is too small. Excessive thinning, cracking on the outside of the bend, or internal wrinkling. The visual is a great reminder that poor bend design leads to part failures or expensive rework. We also calculate bend allowance, which tells us how much material is needed in the bend to create accurate part patterns. This is influenced by radius thickness and a property known as K factor, which represents the location of neutral axis during bending. Finally, we must consider material orientation. So as we discussed in anisotropy, rolling aligns grain in one direction, which affects how the sheet behaves when bent. So bending along grain can cause cracking, while bending perpendicular improves the formability. So this is especially critical for high strength alloys. So we can see that orientation affects the bend quality, reminding us to plan the layout carefully. So designing for holes, the diameter should be at least equal to the sheet thickness. From the edge of the sheet, the distance should be 1.5 times the thickness. And between the holes, we have to leave 2 times the thickness. So also we have to consider that while we are placing 2 holes close together, it can cause material tearing or distortion during forming. And if the holes are gonna involve fasteners, we have to take into account the tool clearance we need to ensure around the hole so that the fastener tool can properly do its job. So from a bend, the distance should be at least 2.5 times the thickness plus the bend radius to avoid warping during bending. Bend reliefs are important when bends end near the edges or cutouts. Without reliefs, the material can tear or stretch unpredictably. As a design guideline, the relief length should be at least equal to the bend radius plus the material thickness, and the relief width should be no less than the sheet thickness. The rounded ends further reduce the stress concentration and tearing during bending. So you can see here how there are two different parts with one which has bend relief and one without. It's kinda actually not feasible to even manufacture parts which don't have bend relief. For slots and notches, the width should be at least the material thickness. Keep them two thicknesses from edges and four from bends. Notches should have a corner radius of 0.5 times the thickness and should not be too deep. If they are placed too close together or too near edges, they can act as stress risers and initiate tearing during forming or under load. Also, if fasteners or hardware are planned near these features, additional spacing must be required in order to accommodate the initiation tools and maintain structural integrity. Tabs should be at least two times the thickness wide and placed far enough to prevent buckling. So from a DFA perspective, tabs allow for simplified part alignment and reduce the necessity for secondary fixtures during assembly. They are typically created as small extensions during blanking and later bent to help with tasks like fastening, slotting, or securing parts in temporary position. So tabs are commonly used in enclosures, brackets, and chassis structures. However, if tabs are too narrow or closely spaced, they may fail during forming or assembly. Poor design tabs can complicate automation or lead to part deformation, making them a critical feature in DFM and DFA integration. So we discussed about general design guidelines, and now we can move on to stiffening techniques. So gussets are triangular reinforcement added at junctions or corners to strengthen a part without adding much weight. From a DFM perspective, they increase rigidity without adding an extra component. So if we are not including a gusset and you want to make the L shape rigid, you might have to add another material and weld it together or fasten it. However, from a DFA standpoint, they might complicate the assembly if not aligned with joining features or tool axis. Flanges and lips are bent edges that add stiffness and provide clean surfaces for fasteners, rivets, or welds. From a DFM perspective, they increase the structural integrity without extra parts. In DFA, flanges help align parts during assembly. Hems, which fold the edge back onto itself, are mainly used for safety and aesthetic purposes, which eliminate sharp edges. So I have seen them in scooter body panels where hems are used so that sharp edges are eliminated basically. So curling forms a smooth looped edge which removes sharpness and improves appearance. It's commonly used on the edges of panels, doors, or consumer-facing products. Curling is typically done using a curl die that bends the edge into a near complete circle. Design guidelines suggest that maintaining a minimum curl radius and ensuring sufficient spacing from nearby bends or holes to prevent distortion or thinning. Proper curling enhances safety, reduces handling injuries, and improves the product aesthetic. You can go through the design guidelines that are listed here. Ribs are basically raised lines on a flat panels that increase the moment of inertia by improving the resistance to bending and buckling. They are typically formed using matched male-female die sets. From a DFM perspective, ribs add stiffness without increasing the material thickness. In DFA, properly positioned ribs can help guide mating parts or resist deformation under assembly forces. However, poor rib placement can interfere with parts nesting or complicate tooling access during assembly. So now you have taken all the design guidelines into consideration. You got your perfect part. Now nesting is the last piece of the puzzle. Nesting is how we lay out our parts on metal sheets before cutting or forming. So good nesting improves material efficiency, reduces scrap, and shortens the cutting path. This not only lowers cost but also supports faster production and more sustainable manufacturing. One final detail is that when we are designing shear features like interlocks or breakaway tabs, we have to ensure that the width is at least 2 times the sheet thickness to develop enough shear strength during separation. It is important to nest parts while considering grain direction, bending locations, and spacing. Proper nesting helps us make the most of each sheet, especially in high volume production. Now let's take a look at how we estimate the cost of a die set in sheet metal format. So die cost is primarily influenced by two things: the unusable area between the guide pillars and the manufacturing complexity of the part. So in general, the cost of die set is CD, where CD is the die set purchase cost in dollars and AU is the unusable area in centimeter square. So we start with a fixed base cost of 120 and add a variable cost that scales with the area. The first plot here virtually confirms this linear relationship between area and cost. As the unusable plate area increases, the die cost rises steadily, but area alone does not tell the full story. So also considering complexity of the part, we use the formula of XP, where XP is a non-dimensional complexity factor and P is the perimeter which will be sheared, while L and W are the length and width of the smallest enclosing rectangle. So the complexity factor increases with irregular part shapes or higher perimeter to area ratios. So the second graph here shows how basic manufacturing effort measured in points increases with complexity XP. So the more complex shapes, even with similar areas, will be costlier and harder to tool. So the key assumption here are that the material of the die is standard tool steel. The process uses conventional guide pillars and press setup. The cost model assumes mild volume production, not amortized over high volume runs. Now let's take that further with manufacturing point estimation, which adjusts the base effort using correction factor for die duration and punch plan area. So the final manufacturing point score, which is denoted as MP, where MPO is the base point value we get from part complexity. FD is the factor that accounts for die plate thickness. FLW adjusts for the plan area of the punch. And the die plate thickness correction factor is calculated with the formula of FD, or there's a minimum value of 0.75 which is taken, like whichever is larger is taken. So we now need to compute HD, the required die plate thickness based on wear and stiffness requirements, which is HD is given by the formula you can see below. So U is the ultimate tensile strength of the material. UMS is the strength of annealed mild steel, which is used as a baseline. V is the production volumes, which is in thousands. H is the sheet thickness in mm. So as the production volume or material strength increases, or when the sheet is thicker, the die needs to be stiffer and more wear resistance. Hence HD increases and so does the cost. A commonly used assumption is U upon UMS into volume into H square, which gives us HD of about 25 mm. This simplifies the analysis for average conditions. Once HD is known, we plug it into FD and finally get the MP, which feeds into the total tooling effort or cost. So in summary, this framework helps us link physical material and production variables like strength, thickness, and volume directly to the die cost and tool life. It ensures the tooling is robust enough for the application without over-designing or overspending. So the base manufacturing score is noted by MPO, which is given by the equation below, where here L and W are the enclosing rectangles length and width in centimeter, capturing the footprint of the flat pattern. And D is the depth of the formed part. If the depth is less than 5 centimeter, we still use 5 as the minimum, which ensures that shallow parts don't get underestimated in effort. The formula basically scales the base points with part size and depth. So larger, deeper parts need more material flow, tooling control and press tonnage, hence the score increases. Next, we add the effort due to bending operations, since each bend adds tool complexity and setup time. That is given by the equation of MP, which you can see. LB is the total length of bend lines across the part in centimeter, while NB is the number of unique bends or stations. So this equation gives us a clear way to quantify how much extra effort each fold or bend adds. So longer bends take more press energy, while greater number of bends mean more tool changes or stages on the operation. These two scores, base manufacturing and bend effort, are combined with earlier correction for thicknesses, punch area and complexity to give us a comprehensive die cost estimation. So let's say we are given the base manufacturing point score MPO, which is 30.5, and calculated using the parts envelope dimensions and depth. So the plan area is length into width, which we'll consider 300 centimeters square. This gives us an area correction factor FLW of 2.5. This comes from the graph shown on the right and varies based on complexity and punch area. Next, we calculate the die thickness, which let's say HD is 26.6 mm, based on the production volume, material strength and sheet thickness. So plugging that into the correction formula, we get FD is equal to 1.03. Now we calculate the adjusted manufacturing effort, where MP is 78.5. The die set cost is calculated using the CDS formula, which comes out to be 390, where 750 centimeters square is the usable guide pillar area. Now we calculate the total die cost by multiplying manufacturing effort with the cost per point, where here we have $40 per point. So the total die cost comes out to be $3,530. We also analyze the material efficiency, where the part area is 251.7 centimeters square and sheet area which is required is 316.9 centimeters square, which gives us a scrap rate of 20.6%. So this example shows us how each factor, geometry, material strength, production volume and part complexity feeds into the comprehensive and scalable cost estimation framework for tooling. So this kind of insight is invaluable in design for manufacturing decisions. Let's consider the time estimation which adds up to the die cost. So the force required for shearing is given by the equation of F, which is 0.5 into U into H into LS, where U is the ultimate tensile strength of the material, H is the gauge or thickness of sheets, which is in mm, and LS is the total shear length, which is also in meters. This gives us a shear force in Newton, which helps us determine the press force which is required. So once we know the required force, we'll refer to the table 9.3 to select the compatible press machine. So this table gives us the press bed size and force range, operating cost per hour, stroke length and stroke per minute, which determine our production speed. So for instance, if our required force is around 1750 kilonewton, we would select the press with an 85 centimeter depth, 150 centimeter width. So this press has an operating cost of $105 an hour and a speed of 35 strokes a minute. So let's say our part requires 1 stroke per cycle. So the cycle time becomes approx 1.7 seconds. Hourly output would be around 2100 parts per shift. With this, we can estimate both production time and press operating cost, which helps us decide whether a large speed or a large press force is economically justified based on what our volume we want to do or complexity of our part. So these values feed into both direct labor cost and capital equipment planning and ensures our forming line is optimized for speed, force, and cost efficiency. So we have looked at shearing. Now let's explore for other bending, shallow forming, and embossing processes, which are also crucial in determining the die size, press force, and time. So for wiper die bending, an approximate bending is given by the two formulas which you can see below, where U is the ultimate strength of the material, H is the thickness, LB is the total length of the bend, and R1, R2 are the radii of punch and die profiles. So for shallow forming, like drawing a shallow dome or dish, the required force is given by the formula we can see below. Theta is the wall angle of the form feature. Force increases as the wall angle gets steeper or material gets thicker. So finally for embossing, which involves pressing fine features or logos into the surface, the force is determined by F is equal to phi U into A, where A is the area to be embossed, phi is the constraint factor which is greater than 1 according for extra resistance due to confined flow. So these formulas help us determine the press capacity needed and time per operation. More force generally means slower cycles or more robust tooling. That in turn feeds directly into both cycle time and die cost. So by calculating accurate force for each operation, we make informed decisions about machine size, tool material, and throughput, which ultimately optimizing both performance and cost. So to complete the time and cost estimation, we also need to factor in loading and unloading time and ultimately calculate the cost per part. So the time estimated to load and unload the part is given by the formula, the first formula, which is in seconds. So here L and W are again the overall length and width in centimeter. So this equation accounts for handling time and scales with part size. For blanking and piercing operations where auto ejection is used, only 2/3 of this time is applied since parts are ejected automatically. So for bending, however, the full cycle time applies because parts are often removed manually to prevent damage or warping. Once we know the time spent per press station or operation, we can compute the cost per part, which is CP, using the formula which we have given below. T is the time of operation per second. Um, R is the press hourly rate in dollars. This gives us a very detailed and operation specific way to estimate forming cost per unit, letting us directly compare process routers or tooling choices and justify automation investments or press selection decisions. So let's wrap up the time estimation by discussing progressive dies, which combine multiple operations like shearing, piercing, and bending into a single automated process. So the total force required here is sum of the forces of all the operations in the die. Now, if we are designing a progressive die, say for 4 stations, we also need to allocate the physical space. So that is calculated by 4 into 100 mm plus 3 into 2 times the thickness. So 3 is the gap between the stations and the formula gives us a total strip length of like 418.5 in this case. So this is critical when designing strip layout and estimating blank feed per stroke. For cycle time, progressive dies operate at a high speed, which is given by 60 upon strokes per minute. We also have the cost per part, which is like T upon 3600 into R into 100, where R is the press hourly rate. So this equation captures how long the press runs per part and converts it into a dollar figure. So finally, it is important to note that progressive dies are significantly faster and more cost effective per part compared to using a multiple individual dies. They reduce handling time, increase throughput, and are ideal for high volume production. That's why they are widely adopted in consumer electronics, automotive brackets, and appliance components. Anywhere speed, like when everywhere where speed and repeatability matters. To wrap up everything, Sheet metal forming is the powerful process that reshapes flat metals using plastic deformation when no material is added or removed, just skillfully redirected. So it's the backbone process in industries like automotive, aerospace, electronics, and appliances due to its strength, precision, and efficiency. By applying the design for manufacturing principles, we ensure better part manufacturability, enhanced structural performance at lower cost. Let's quickly revisit the key guidelines. Always maintain an appropriate bend radius to avoid cracking. Respect distances for holes, bends, and edges to prevent tearing and deformation. Incorporate stiffening features like flanges, ribs, and gussets for added strength. And don't forget to account for material orientation and anisotropy, as these factors affect how the part will behave during forming. Efficient nesting and accurate cost estimations are essential for scaling up the production while staying cost competitive. Ultimately, good DFM doesn't just make parts, it makes better parts, smoother production, and stronger engineering decisions. Thank you. So these are the references where 1 and 2 will tell you about the design guidelines. The third reference is actually about nesting, which is like a SolidWorks nesting video, which you can watch, is quite interesting. And then we have a book that we refer. Yeah, thank you.